So welcome you all in this second set of webinar. And on behalf of the Civil Department of Anand Institute of Higher Technology, we are going to welcome you all to in this session of corrosion mechanism in concrete structures. So this is a 2 days webinar. So the webinars will comprises of two parts, part one and part two. Part one, yes, part one and part two, as mentioned as day one and day two. So the module on this webinar are comprises of these five divisions. So the first one is you can see here that how the corrosion initiates in a concrete structure. We see in brief about the corrosion that mechanisms of concrete structure, and after that we see that carbonation induced corrosion. The third one will be the chloride induced corrosion, and the fourth one will be that conditional condition appraisal. So how to assess the condition of corrosion, or the how to assess the amount of corrosion in any that embedded rebars. And what that the last one is comprises of, the last topic is comprises of the preventive maintenance and the need of preventive maintenance as well. So already we have conducted one webinar based on the repair techniques in civil engineering works. So in that also we have explained somewhat in brief about the corrosion mechanism. So here also we are going to explain in detail about the different corrosion mechanisms and how it initiates in the structure, concrete structure, and what are the effects. And after discussing all those things, we will go for that carbonation induced corrosion and chloride induced corrosion. Once again, I want to thank the management of our institution for giving us this opportunity to share all those things with you people. So before going to start the session, I want to clear one thing with you, all the participants. That these are all the things we are going. I'm going to share with you. It may be known as well. It may be known for you. So it's like a recapping of all those things based on this particular topic. So before the start of this corrosion in mechanism, or the corrosion, how the corrosion happens in concrete structure, I want to explain, or I want to say you that the cost of corrosion of our country. Why we have to know all those things? Because if we don't used to understand this particular statistics, we may not be able to know the importance of knowing the corrosion mechanism of concrete structure and how to resist all those things or the corrosion in the concrete structure. So according to the census of 2014, it has been seen that about 4 lakh crore rupees per year annually we are expending for doing the repair work, particularly for corrosion process. So it's a huge amount. So we are expending a amount of 4 lakh crores annually for doing the repair work for corrosion. And it has been also seen that it hits 3 to 4% of GDP, of our GDP. So the whole repair work and the corrosion, the corrosion cost of our country is 3 to 4% of the whole GDP. So it's not a matter to neglect. We have to be very careful when we are going to do any repair work as well as new construction also, because it's a huge amount we are expending and we are utilizing for fixing all those problems. And it has been also noticed that 50 percentage of the total construction budget, out of these 50% we are using for only maintaining the corrosion work, only doing that fixation work for corrosion. So it is also not good. The cost of corrosion covers about the half of the total construction cost. So this is also a matter to think about. And it has been also seen that 50% of the structure is hitting corrosion within some 10 years of lifespan. So it's not good. Even the structure is also designed for more than 50 years of lifespan. It has been noticed that within some 10 years of lifespan, the structure is suffering from huge corrosion or any types of the deterioration mechanisms. So this is also not good actually, because this may happen due to poor workmanship or that quality of materials that we are using for the construction process. So we have to be very careful. We have to know all those things, because otherwise until and unless we cannot able to understand the importance of the corrosion that is happening in concrete structure. And the last two parameters, you can see that 30% of the steel is utilizing for doing the repair work, and 40% of cement is also used for doing the only repair work. So you may say that these are the huge amount, but it has been cross-checked with the manufacturing companies for both that steel and cement. It is somewhat quite similar. That so these two numbers, that this 30% and 40%, the 30% of steel and 40% of cement is quite alarming. So these two numbers are quite alarming, you can see. And also here the 3 to 4% of GDP. So we have to reduce it. So for reducing all those things, we have to have a very good protection, that corrosion protection strategy. We have to maintain these things so that we can reduce these costs. And nowadays we are having advanced technologies also to resist all those corrosion mechanisms, to protect or to prevent the structure from corrosion. So one point I want to mention you here is, when we say the protection from corrosion and prevention from corrosion is quite different. So prevention means from the starting stage itself we have to prevent the structure so that corrosion, it may take a long time to initiate the corrosion. So we can delay the time of the rate of corrosion by preventing the structure from the initial stage itself. And protection means once the corrosion initiates in a structure, we have to stop it. How to protect the structure from corrosion? So there is a significant difference in between that protection and prevention. So we have to adopt all those things very accurately for getting a very desired and durable structure so that we can reduce this cost. So the main message from this slide is to inform you that we are wasting a huge amount of money in repair work. So if we follow the protocols, if we follow the very good repair work and very good construction workmanship also, if the quality of the work, if the quality of the construction, if really it is good, we may not have to suffer, or we may not have to go through these types of critical situations. So okay, so why the cost of corrosion is becoming important nowadays? Because on the daily basis, if you see today, we are constructing more and more important structures, and along with these important structures, we are also constructing that associated structures which are associated to these types of important structures. So important structures, if you say like highways, seaports, airports, the different public projects, that bridges, flyovers, and the associated structure means, so suppose if you are going to construct a road, so along this road there will be some that important structures which are associated with this road. So all these structures, so you can see we are constructing on a daily basis, or today we are constructing, there's a constructing boom now. So we are constructing huge amount of structures, and if we uh, doesn't have a that strategy to control corrosion, then we have to go through and we have to waste much more amount day by day, because we are constructing more and more. Because if the repair cost is going on in such a way, then based on the rate of construction that we are doing nowadays, so the rate of repair work, the rate of the cost of repair work will also increase. As we have seen in the previous slide, it is the census that has been taken in 2014. In the first point you can see, so day by day the cost is increasing. So why it is increasing? Because we are constructing more and more structures, and as we are constructing more, the structures are getting distressed within a very short period of time, and we are end up by doing some repair work. And even it has been also seen that nowadays the repair work is also not durable, and again we are going on the same place to do the same thing again. So in a daily life basis, in a cyclic basis, we are wasting a huge amount of money only for this repair work. So this is also a hindrance in the infrastructure development of our country. So we have to reduce this repair cost so that we can utilize this amount of capital to develop our society, to build up new infrastructures. So if you can see the corrosion map of our country, so India is having a different geographical. We are having different geographical locations in different areas, and the level of ground, as well as different weatheric and climatic conditions as well. So probably when we think about corrosion in any type of concrete structure, in most of the cases, it comes in our mind that the structure might is suffering from that chloride induced corrosion or that chlorination. So this is because probably maybe we are having a very long coastal line, about 7,000 kilometers of coastal line we are having. So this may be also the reason we are thinking like this. But besides this, also we might have that carbonation induced corrosion also in this region. So we are having a huge amount of that coastal line in our country, and the structures which are near to the coastal line may suffer from chloride induced corrosion because the atmosphere of this region might have not might have having airborne that chlorides, and also the soil of this particular region is quite rich in chlorine or chlorides. So the foundation also may used to suffer from severe corrosions. So besides this, the carbonation is also that factor in some of the cases, because whenever you will get a humidity, a relative humidity to 60 to 70 percentage of relative humidity, you may see that there are some carbonation induced corrosion as well. So we have to be very careful when we construct structures along the coastal line. And as I told that the relative that humidity of 60 to 70 percentage may also that influence the structure to have a carbonation induced corrosion. So if you see that in a structure which is away from the coastal line or interior of this part of this, suppose in this area, in the moderate zone or in the mild zone also. So if you consider in a structure like that, at that time you have to consider the local exposure. So there may be some chemical plant, or if you are constructing some chemical industry which works with salt and all. So the ambience of the atmosphere near this structure may be rich in that chloride. So there also you may use that chloride induced corrosion. Even though this region is away from the coastal line, you may have a that chloride induced corrosion. So at that time also we have to consider the local exposure. So if there is any chemical plant is there or like that, we have to see that before construction itself we have to see that what type of the atmosphere is there, and based on this we have to select suitable materials and different suitable strategies. So now I'm going to explain you in very short how the iron get corrodes, or the where how a steel get corrodes and why. What is the reason behind it? So when we manufacture steel, we manufacture steel from iron ore, and this iron ore first from this we used to give a heat energy to this iron ore for getting it into the to melt it. So in the second stage we are putting these things into the blast furnace for we are giving heat energy, and we are getting the molten material. After getting the molten material, we are remolding all those things and we are die cast. Based on the shape, we used to mold the material to get particular shape, our desired shape. Suppose if you need a rebar, we used to shape it into the cylindrical bar. If you need channel sections, eye sections, or any angle section, based on this we can do molding. So here in this stage, I just wait, I'm showing you. So in this stage we are giving a we are giving a huge amount of heat energy to the material in the sense to the iron ore. And after giving heat energy, after getting the molten material, we are giving some mechanical energy here in this part for getting the molten material into a particular shape. So at the end, when the product comes, when the product comes at the end, the product is having a maximum energy. So if you expose these types of materials, or any material which is having the high energy, or the residual stress is more on the surface, at that time the material become more reactive. So as it becomes more reactive, when you place all those materials in any extreme environment, it will surely undergo corrosion mechanism or corrosion process. So when this iron or steel is exposed to open environment, that due to some moisture and oxygen, and it may be that marine environment or any type of extreme environment, when the material used to expose, it suffers corrosion under these following reactions. So you can see the reactions here, that one, two, three. So after undergoing all those reactions, at the final stage, we used to get Fe2O3, which is quite similar, which is having a quite similar structure to the iron ore. So here you can see that Fe2O3 after getting the final reaction, the reaction product, which is quite similar to the iron ore. So the metal is going back to the initial state of energy, or the lowest state of energy, by this process. So that is the reason because why iron corrodes or steel corrodes, because uh, basically from the lowest state of energy we are bringing this material to the highest state of energy by giving heat energy here, sorry, uh, by giving heat energy here, and by giving mechanical energy here. So by giving after giving energies to the material, it the final product is having a huge amount of energy, and a material which is having a huge amount of energy and high residual stress over the surface, these types of materials will be quite reactive, high reactive materials. So when you expose this high amount, or that high reactive materials to any type of extreme environment, obviously this material or this element will suffer that corrosion. So here you can see the reaction process here from 1 2 3. After getting the that final product, it has been seen that the final product what we are getting is quite similar to the iron ore. So the material is going back to the original stage or the initial stage after the whole corrosion process. So it's like the corrosion is like some extractive metallurgy in reverse directions. So see here, you can see that these two that element is quite same. So we are getting a quite similar structure like as iron ore after the corrosion process. So now what we can do is we can control the rate at which it goes back to the initial stage. We cannot stop it. I don't know. Up to now there is no nothing or there is no discovery so that we can stop it totally. But we can slower the rate at which it reaches to the initial stage. For example, if you take a that stainless steel. So it will take time to reach back to its original stage. In some of the cases, if the quality is good, it will take a really long time to reach into the initial stage. But now, if you take a mild steel, it may react more in a high rate, and it may reach to the initial stage quite fast. So the message from this is we can control the that reaction process so that this controlling is all the prevention and protection method. So we can control the reaction rate, how it goes to the initial stage. But up to now, there is no nothing that technology we can stop it totally. So, okay. So, in brief, I want to discuss something about the steel. So, whenever we talk about steel, in most of the case, we may think that steel is homogeneous, but exactly steel is not a homogeneous metal. You can see if you go in the macro structure level of steel in the picture in the left side, you can see here that there are n number of that materials are present in this. You can see here some materials. You can see here some laminar type of materials are there. Laminar types of materials, sorry, I can show you clearly. Here you can see some laminar type of that elements. So these types of different elements used to create n number of faces inside the that inside any steel or iron elements in microstructure level. So you can see here the main thing to show you that the iron is the steel which is available like as mild steel or TMT steel, even the pre-stressing steel also. They are not containing only iron. They are also containing that different types of elements. You can see here even though the amount of iron is quite high, but they're also having different types of elements or chemicals present in the steel, which may be the which not maybe which is the reason why the corrosion happens. So actually that's what that metallurgy can do. We can modify all those things, so by we can modify these things and all to get a good quality of steel. So for by doing some techniques in metallurgy, we can reduce all those things and we can bring the element into quite homogeneous, so that we can remove all those chemicals to uh, form the different phases. So if we have different phases like this, you can see here in this microstructure, we can generate the corrosion cell can generate in these types of different phases, because the different phase will have different properties, and automatically the corrosion cell will generate. So we'll see in detail about the corrosion cell in the upcoming slides. So now if we talk about concrete, concrete is, you can see, is comprises of the main important thing of concrete is that calcium silicate hydrate, CSH. This is known as the binder of the concrete, or the which is the important material in the concrete, giving strength also. So beside then these we have calcium hydroxide, sodium hydroxide, and potassium hydroxide. So these types of chemicals are quite alkaline in nature, and we are getting for that particular reason the pore solution of concrete is somewhat alkaline in nature. And beside this we are also having a number of complex chemical compounds. So now it has been seen that the pore solution of concrete is quite alkaline in nature, and the pH of a typical concrete pore solution lies in between 12 to 13.5. So you can see here that in the pH scale, the pH of the concrete lies between 12 to 13.5. So this is the one reason why we can able to use steel rebars in concrete, and this passivity protects the steel to get corroded. So on the next slide, we'll see that how the passive film or passive layer generates in a rebar when we embedded a rebar in a concrete system. So you can see here, yeah, like this. When we deep that rebar, steel rebar in a concrete system, the it has been seen that a protective film, that green color film you can see here, that green color film, it like this. So it's the imaginary diagram I showed you. So like that, a film is, or a protective layer is generated in a concrete which is very thin and invisible. So this layer helps the that rebar to protect itself from corrosion. So due to this high pH of the concrete pore solution, the river can able to stay there for a long time without any corrosion. So this is one of the important reason why we can use steel in concrete. And besides this, one more important reason is also there, which is not coming in this topic. So that important reason is the coefficient of thermal expansion of both concrete and steel is quite similar. So why that this particular parameter is important, because we all know that the reaction, the hydration reaction, which happens when we add moisture to the cement or to concrete. So due to this hydration reaction, a huge amount of heat is produced, which is a exothermic reaction. So due to this heat, the in a concrete mass, so there may be some expansion of the concrete in plastic stage, and due to this heat, there may be a construction in the steel as well. So if the rate of contraction, expansion and contraction, so when the heat goes, it will again try to contract to its original shape. So if the rate of this expansion and contraction is not same, then there may be some formation of cracks, or the immature cracks in the concrete surface. So it has been seen that the coefficient of thermal expansion. So by this parameter, we can understand that the rate of contraction and expansion of any element due to when they are undergoing any that heating process. So that particular parameter for both steel and concrete is same. And this is one important, and one more important is due to the presence of these that the different types of alkaline compounds in concrete structure and in concrete solution, the pH of the concrete solution generally is quite high. So due to this pH, due to this high pH, or due to this alkaline nature of the concrete, it saves the that steel bars to get corrosion, to get attacked from corrosion. So so if we want to corrode the bar, or if the bar wants to get corroded, then we have to break this specific film, or we have to break this protective layer. So when this protective layer gets damaged, or when this protective layer, when some deleterious elements, or when that I suppose chlorine, that chlorine, or that carbon dioxide, or whatever the things used to get enter into the concrete surface, and when it breaks this passive film, then only the corrosion initiates. And once the corrosion initiates, it is a continuous process. So we'll see all those things in the upcoming slides. So here the main thing is that, so due to this passive flame, we can use steel in concrete, and this passive flame is helping the steel bar to protect itself from getting corroded. And to initiate corrosion, we have to destroy it. So what are the things that destroying this passive flame? So here we'll see all these things in the next slide. So here the depassivation or the corrosion can happen when it is exposed to chlorides or carbon dioxide. When any structure is exposed to chloride or carbon dioxide, these types of depassivation. So this is passivation and the depassivation. So with the presence of that oxygen and moisture, this is quite important. If we can that get rid of any of these, either oxygen or the moisture, we can stop corrosion. But generally it is not possible. It cannot happen. So we cannot remove all those things from our atmosphere, so it is not possible. So the depassivation may happen due to that when we expose these things to that chloride rich environment or carbon dioxide rich environment. So the structure, you can see in the that photographs, the structure which is there in the that marine structures may suffer from chloride induced corrosion. And these types of structures where you can get a 60 to 70% of relative humidity, and the where the local concentration of carbon dioxide is more, at that time also you can get the carbonation induced corrosion. So provided here, the important thing is the humidity should be in between 60 to 70%. If the humidity is more than 70%, you may not see chloride induced corrosion. If the humidity is less than that 60 or 50%, you might not have seen that carbonation induced corrosion. The main important thing here is that the presence of moisture in oxygen for the both of the cases is quite important to initiate corrosion. So now, what are the essential parts of a corrosion cell? So before going to enter into this, I want to say you that for getting a corrosion cell to be completed, we need some elements which will complete the corrosion cell. So we need to have a anode, we need to have a cathode, and we need to have a ionic conductor and also a electronic conductor. So how it happens in the corrosion things, the corrosion cell, I'm going to explain you. So in the anode parts used to get corrode. Let me annotate. This anode part, it gets corrode. You can see that corrosion happens in this part. And from this anode, the that electrons are, sorry, some problem. Just wait. So you can see here the metal surface was like that, and it has been corroded. So you will find the corrosion in the anodic part. So from this anode, the electrons are getting transferred to the cathode, and in this interface of this anode and cathode interface, you can see that the ions are getting transferred, and the raster getting formed in the cathodic side. So these types of things can even happen in a scale of millimeter range also. So if we can remove any one of these element, either anode or cathode, or that solution, electrolytic solution, or the electronic conductor, we can also stop corrosion. But here also it is not possible. We'll see the detail of the corrosion mechanism in the next upcoming slides. So here the thing is, to complete the corrosion cell we need to have, so these are the things we need to have. So where in a concrete structure, the the metal or the steel is that taking part of the electronic conductor, and the concrete solution is acting as an electrolyte, and that metal itself is acting as anode and cathode. How it is acting, all these things we'll see in the upcoming slides. So, what are the reactions that are happening in the anodic side and the cathodic side of a corrosion cell? So, in anode, the iron is getting diffused into Fe2 plus and 2 electrons. So, as I mentioned in the earlier side, so in from that part you can see there is a corrosion. So, the metal from anode is getting degraded, it's getting degraded from this part, and it is diffusing into Fe2 plus and electrons. And on the cathodic side, where there is enormous amount of oxygen and moisture, these electrons are going that particular cathode through the electronic conductor, and there this electron is getting mixed with these that oxygen and moisture to form hydroxide ions. Later these hydroxide ions and this Fe2 plus reacts to form the rust. So here you can see that this picture. So in that picture you can see the presence of both, how the presence of the moisture and oxygen plays a vital role in corrosion. So if you see that this part of the pillar or the pier is suffering from severe corrosion. So the reason is, if you go up in this part, you may not find that much of moisture, and if you go deep here, you may not find enough oxygen. So this is the particular region. This is the particular region where you can find that enormous amount of that both the presence of moisture and oxygen. And due to this wetting and drying action, the waving action of the water is helping the chloride to ingress. So these are the so I found this picture somewhat informative to make you explain this thing, the role of the presence of both moisture and oxygen in a corrosion cell. Here also you can see the structure is suffering from severe corrosion due to the presence of the marine environment. You can see that this part is suffering from severe corrosion, because here this in this region there is a presence of both oxygen and moisture in abundant amount, and the that wetting and drying action is also initiating the chloride to enter the concrete very fast. So in detail, I'm going to explain you now how the corrosion mechanism happens in a that steel concrete system or still water. Water is also electrolyte. So like that, how it happens. So in the anodic part, the anode is going to degrade it. So you can see a cross section loss in the anodic part, and from this anodic part, the iron and the Fe2 plus, the iron is getting diffuses into that Fe2 plus and 2 electrons. The iron is getting diffuses into Fe2 plus and 2 electrons. Let me annotate. iron is going to diffuse into two parts, Fe2 plus and two electrons. And these electrons are moving towards the cathode, and with the presence of oxygen and hydrogen, it forms OH, and there is a kind of movement of this OH. And when this Fe2 plus and this OH reacts, we get FeOH2, that the rust. So for understanding purpose, I show you in this thing in a very big scale, but it may also happen in a very minute scale, in a very that micrometer scale also. So the message from this is that the anode and cathode can exist in the same piece of metal. So now we are going to see in detail what we have seen in the that last element and all. So I have explained all those things very briefly. So now we are going to see how this thing can also happen in a same piece of metal. So generally in a electrolytic cell or in any type of electrolytic reaction, we have been seen that the anode and cathode is separate. But in case of corrosion, the anode and cathode maybe exist in same piece of metal. How it happens, let's see. So in addition to the presence of an electrolyte, there must be a potential difference between the anode and cathode. So first thing we have to notice that in between the anode and cathode, to get there may be some potential difference to complete the cell. So the potential difference, so if there is any potential difference in between the two phase of a similar material, we can get a cell. We can have a anode and cathode in the either side based on the potential difference. So because the potential at cathode and anode will not be the same. So the following may be the reasons. So the first reason is due to the non-uniformity of the metal, and the second reason is due to the non-uniformity of the electrolyte, and the third one is due to the non-uniformity of the physical conditions. So we'll see one by one. So if here you can see the due to the non-uniformity of metal. So as I show you earlier itself, the microstructure of steel, it's not same. We are having n number of chemicals and the different phases inside the steel uh, metal. So here you can see here we are having that ferrite phase. We are having ferrite phase, and also we are having that cementite phase in a steel. So you can see this cementite phase and ferrite phase, that n number of things are there. So which are creating different phases inside a steel. So there may be some transfer of electrons from the ferrite phase to the cementite phase. So the ferrite phase may act as an anode. So we'll have a corrosion over here. So you can see the cross section loss and the formation of rust in the cathode part. That is that the cementite phase may act as a cathode. So like this, there may be a difference in the potential, which may lead to corrosion. So due to the different phase, that the potential will be different, and it may also lead corrosion. So this is the reason based on that comes under non-uniformity of the metal. So now we'll see that non-uniformity of the electrolyte. So that here in this concrete steel concrete system, the electrolyte is concrete. So the concrete is, we know that concrete is not a homogeneous mix; it's a heterogeneous mix. So already, even though we do that a very good mixing homogeneous, we used to get a homogeneous mix, but in real practice, it is not possible to get a homogeneous mix. So in the examples, if you see that if the that bar which is embedded in the concrete system is having a high that acidity in one part, I just annotate you. If the acidity of one part is more, if the acidity of one part is more, and if the acidity of another part is somewhat less, or it may be more alkaline, so the part which is having more acid in nature may suffer from corrosion. So these are due to the non-uniformity of the alkaline due to in acid, due to acidity and alkalinity. So this is also a reason why we can get corrosion due to non-uniformity of the electrolyte. So the second example, if you see, due to the presence of chloride, that it is not that mandatory that the the presence of chloride or the what to say, the percentage of chloride will not be same that throughout the concrete structure. It won't be homogeneous. So where there will be more concentration of chloride, you have a corrosion at that particular region. Suppose if you have an aggregate here in the concrete system, so the chloride may not reach in this part, so it may turn back like this and it may come here to so the accumulation of chloride in this particular region will be more. So if the that accumulation of chloride is more here, it may cause a corrosion. So it may generate a different potential in between this part and this part. The potential may be different, and a corrosion cell can automatically generate. Here also one more example. We are using lot of admixtures like as corrosion inhibitor, like as example calcium nitride. So we are using n number of that corrosion inhibitors nowadays to resist corrosion. So if the uniformity of the inhibitor is not similar across the concrete mass, you can also have a that generation of cell. So if the inhibitor is suppose in that particular place the amount of corrosion inhibitor is more, so you won't find any corrosion here, and here the amount of inhibitor is less, so this particular region may act as anode. So you can get a corrosion over there. So these are also some of the examples of non-uniformity of the electrolyte. So here again I'm going to remind you that electrolyte means that concrete system in the steel concrete, when you used to talk about steel concrete. Okay, now we'll see about the non-uniformity of the physical condition. So here also the same thing happens. So this is an example of the presence of meal scale. So this, suppose this is that steel, and this is a steel, and this is a meal scale, and this is the mold. So when you will remove the mold, you will find a steel structure or steel surface structure of like this. So nowadays, in most of the cases, we used to remove this meal scale, but still there may be some the presence of meal scale on the steel surface. So which may create a that corrosion cell in that particular region. So and it can generate corrosion. So some crevice corrosion can happen through this particular material. So the chloride or the deleterious materials can get ingress through these that joints and all. So due to this, there may be some electronic transfer in between the this mill scale and steel. So this will have a separate potential, and this will have a separate potential. So automatically there will be a generation of corrosion cell. So these are the reasons why we can have a that cathode and anode in the same piece of metal, due to that non-uniformity of the materials and due to the non-uniformity of the electrolytes. So it may be I just showed you just two three examples. So it may be in a different factors also, due to the that heterogeneous mixtures. So it is not possible to achieve a perfect homogeneous mixture in nature for the for the concrete mix. So due to this, there may be some generation of cell, corrosion cell in the embedded rebars. And here also that uniformity, non-uniformity of the physical condition can also that create a problem like this. It can generate the presence of mill scale in steel or any other compounds may also create a potential difference, creating a that corrosion cell. So now here also one more case. So if there is we know that the surface of the steel is not smooth. There are a lot of ribs, and that due to this non-uniformity of the rebars, there may be some generation of voids, or in between the rebars and the rebar concrete interface. There may be some accumulation of void, and the void may be of that comprises of half air and half moisture and all. So if the things are happening like this at that particular that place also, there may be some generation of corrosion cell. So this is one example taken from the that laboratory of IIT Madras. So they have did like this. They have casted a sample and they exposed the sample to chloride induced for the chlorination. It has been seen that in the imaging, some there are some formation of this voids. There are some voids like structure they have noticed, and after breaking the sample, it has been seen that exactly in the same location there is formation of corrosion. So if there is a presence of voids and all, so we cannot make it stop totally. It may happen like this. So due to the formation of all these kind of voids and due to the non-uniformity of the physical conditions like this, here also we have seen that due to this non-uniformity, there is a generation of corrosion cell in this particular region. So like this, a lot of things can be can initiate the corrosion, or they can initiate the corrosion cell to generate. Okay. So how the cracks generate due to corrosion? So as you all know that while the steel or any that iron I used to get that after corrosion there is a significant increase in their volume. So when the volume increases by about 6 times or 6 to 7 times, it has been seen that after corrosion, due to the accumulation of the rust and all, there is a significant increase in the volume, and the volume of that iron increases about 6 to 8 times. So due to this that volume increment, it will give a that outward pressure to the concrete surface. Since the volume is increasing, it will give a outward pressure to the concrete surface, and due to this outward pressure, the concrete will try to move outwards, to try to move the elements of the concrete will that aggregates and fine aggregates, whatever, it will try to replace from its original shape. And if the stress that are giving due to the that volume increase of the steel, if the stress is increasing the tensile stress of the concrete, then we may see that formation of cracks. So in that picture, in that right side in this picture, you can see. Sorry, I can show you. So in this picture, you can see that there is a bulging of this in this area. You can see there is a bulging due to this corrosion. This bar is giving stress towards the to the concrete towards outside. So there is a bulging. So this volume increment can lead to a significant damage to the concrete structure. So how it happens? So due to this that volume increment, the residual stress will give a pressure to the concrete surface. And suppose if you have a if you have a cover like this. Suppose here you can see, suppose this part is the concrete cover and this is the deep of the concrete. So this cover concrete, this cover concrete will suffer more that stress, because inside there the volume of concrete is more. So sorry, inside the volume of concrete is more. So if you so this cover concrete, you can see that here the cover concrete is suffering from severe damage. So one more example in the left side picture you can see here. So actually this is a stone, and there is the one that steel river. So even due to the corrosion of this river, even the stone has been also got some crack. So if it can crack stone, it can easily crack the concrete structure also, because concrete is a man-made stone. So somewhat we also discussed these things in the earlier lectures. So now there are so primarily we're going to see that there are two types of corrosions, as I mentioned earlier, that carbonation induced corrosion and chloride induced corrosion. So if we talk about carbonation induced corrosion, it has been seen that generally the type of corrosion is uniform in the case of carbonation induced corrosion, and in the case of chloride induced corrosion, the type of that corrosion is that localized corrosion or local corrosion. So uniform corrosion means throughout the whole surface, the corrosion rate and the amount of corrosion will be quite similar. And in the case of localized corrosion, it has been you can see that the corrosion will be at a particular place. It won't be throughout the surface. It will be at a particular place. So, if, like for an example, I have shown you some pictures here. You can see for the carbonation, the corrosion is like uniform throughout the length. You can see the length of the pipe. You can have a uniform corrosion. And in the case of that chloride-induced corrosion, you can see that pit hole is there, a pit hole. So it's like a localized corrosion. At a particular place, the corrosion will start, and it will start mitigate, or it will start progressing out later. So the corrosion, that initiation will be there at a particular point where there is more chloride. So we'll see in details about the carbonation. So there are some these are some ordinary or typical locations where we can see the carbonation induced corrosion. So when there is a suppose the picture which is shown here in the left side, so you can see here this picture. So the when there is a relative humidity of 60 to 70%, as I told earlier, due to the presence of moisture and oxygen, you may have a chloride induced corrosion. So in this you can see that this is one that flyover of a metro city. So in this place you can see the concentration of chloride local. The local concentration of chloride is much more, and already okay, the concentration of carbon dioxide here is more. The carbon dioxide will diffuse into the atmosphere, but locally the concentration here is more. So these types of structure may also suffer from that carbonation induced corrosion or carbonation. So that humidity. So humidity plays a very vital role in the case of carbonation induced corrosion. If the humidity is more than 70%, you cannot have a carbonation. If the humidity is also less than 62 or 55%, you may not have a carbonation induced corrosion. So humid. So in this structure, I want to say, okay, we'll see these things in the upcoming slide in detail. So one more type of locations we can see in this that railway station. You might have seen these types of fences in this railway that boundaries. So you can see very carefully that these minute cracks are there. I have already noticed that marked with the red mark. So these types of corrosion, that cracks are also happening due to that carbonation induced corrosion. So how it happens like this? If you see the cross section of this bar, this elements, the cross section will be somewhat like this. And the concrete, the materials that they're using this for making these types of pillars are that porous mortar. Or even though if it is concrete, the aggregate size are quite small, so these are porous in nature, and due to this porosity, the carbon dioxide easily get enters into this that through the concrete. And there is one river through the middle of this that pillar. That river corrodes and expands, and eventually forming these cracks. So the cracks that you are watching here, it may be in this direction, or it may be in here also, it may be here also, it may be in here also. So these types of cracks are forming due to this carbonation induced corrosion. So now I'm going to say about the mechanism of carbonation, how the the carbonation induced corrosion happens. What is the mechanism behind it? So when the carbon dioxide enters the concrete surface, there is a consumption of calcium hydroxide. So as I had mentioned earlier, due to the presence of this calcium hydroxide, that alkaline elements also, the passivity or the alkalinity of the concrete surface is high. But due to the that when the carbon dioxide enters into the concrete surface, the calcium hydroxide gets consumed to form calcium carbonate. Thus, the concrete becomes acidic in nature. And if the carbon dioxide reaches to the just near to the surface of the river, just wait, near to the surface of this river here, if it is reaches, if the chloride, if the carbon dioxide that reaches to particular this part, so the surrounding of the bar may get acidifies, and if the pH if goes near to 9 or less, the carbonation will start, the corrosion will initiates. So we'll see. So these are the somewhat detailed what are the reactions happened in that carbonation induced corrosion. So when the carbon dioxide enters into the concrete system, first it reacts with the moisture of the moisture which is present in the concrete system. So after reacting with this moisture, there is a formation of carbonic acid, H2CO3. So later this carbonic acid reacts with the calcium hydroxide to form calcium carbonate. Thus, the calcium hydroxide is breaking down and it's forming a calcium carbonate with the release of OH minus, that OH ions, hydroxide ions. So the solution becomes acidic in such a way. And in addition, again, when the calcium oxide, which is coming out from these that CaSH, calcium silicate hydrate, is also getting carbonated with the presence of carbonic acid to form calcium carbonate. Thus, slowly the acidity of that concrete solution increases, and thus the corrosion starts. So, this whole mechanism happens in a uniform way. So that's why we are getting a uniform corrosion of the embedded steel due to carbonation. And these whole mechanisms leads to the reduction of the pH around the bar also, which is also that helping to break that protective layer or that passive film, just initiating the carbonation induced corrosion. So now we can also find the depth of corrosion, up to how much depth. Because see here in the previous slide, the chloride is just getting entered from the atmosphere towards the concrete surface and reach it, and slowly it reaches towards the that bar. So we can find that how much depth, up to how much depth it has been entered into the concrete surface by using phenolphthalein indicator. So in previous stage of your life also, I hope so you have used that phenolphthalein indicator for in your chemistry lab for identifying the acidity and passivity of any solution. So we can simply spray the phenolphthalein indicator, and we can, and after spraying, if there is a change of color, based on the change of color, we can also determine at how much is the corrosion depth. So the phenolphthalein will change its color to somewhat purple or somewhat pinkish if the region is acidic, sorry, alkaline in nature. So when a solution turns into that alkaline solution, the color changes. So here you can see, as I told, that carbonation in concrete is some acidic. Across the periphery of the concrete surface, you can see here across this periphery there is not no change of color. So this means that the pH of this particular part is less than 9 or 9 or less than 9. So this particular region is suffering from carbonation. When the core of the that concrete is having the purple color, it means that the pH is more than that 9 or above. So you can also see one more that this the picture in the right side. This is also data that has been collected from research. So they have very nicely they have shown that how they have differentiated the carbonated area and the non-carbonated area by using phenolphthalein indicator. So easily we can understand that up to how much depth of the concrete the carbonation has been that occurred, or up to how much depth the concrete surface is suffering from carbonation. So this is also one more example on the day basis. If you see on the day, the top left diagram figure, you can see that at the seventh day, the number of days, with the increase of the number of days, how the concrete is suffering from corrosion, carbonation. You can easily see that in the top left picture. Within after 7 days, it has been seen that there is no significant carbonation across the periphery also of the concrete. So the whole concrete system is showing the that purple color. And after 14 days, it has been seen that that outer region of the concrete is suffering from that carbonation. And the 21 days, the situation is much more bad, and it is getting worse and worse with the increase of time. And it has been seen that at the age of 120 days, in the chloride, in the carbon dioxide rich environment, the whole that concrete system is suffering from carbonation. On 106 days, it has been very lightly, or already it has been damaged due to that carbonation. You can see that on the 84th day itself, the concrete is suffering. Not even 84th, in the that 42 day itself, the concrete is suffering from severe that carbonation. Similarly, with some different set of that concrete system, they also have did one more example. You can see in the down right side diagram. Here also, the first 2 days, it has been seen that there is no carbonation, because the whole that surface is whole full and full purple. And slowly, when if the increase of the number of days, the carbonation is increasing, and slowly you can see at the 25th day, there is a huge carbonation through the periphery of the that concrete system. So by using this phenolphthalein indicator, we can easily determine the depth of carbonation. So it's quite easy to understand that up to how much depth the carbonation corrosion or the carbonation is going to happen. So based on this, we can do the repair work also. So we'll see these things in detail in later. So here one more example. Here you can see it has been the data has been collected from IIT Madras. The top left side of the diagram you can see here. This is actually a concrete core that has been collected from the that site, and it has been seen that the concrete core, from this you can I can easily say that the this is actually this is wait I am showing you. This is actually the cover part of the concrete, and this is towards the dip. So it has been that extracted. So here also the same type of that diagram you can see. This is the cover part. This is the cover part, and this is towards the depth. So the carbon dioxide is entering through this zone. So from this, in the top left diagram, I can show there is a embedded river. I can tell you that the river is that very soon the river is going to suffer from corrosion due to this. So easily you can see that by using this, once you collect the core sample from the site, you can easily understand that up to how much depth we have to do the repair work, up to how much depth we have to remove, or we have to do work up to how much depth of the concrete system we have to do the repair work. So from this also, I want to say you one information. When you are going to collect any sample from the structure, or when you are going to collect any core from the structure, that rivers should not be cut while extracting cores for condition assessment. When you are going to take some sample from the field to do some test in your laboratory, be ensured that don't cut the rivers, because once you cut the rivers, you are destroying the structures. So the whole load bearing path will be changed. So okay, so you have to replace the whole system. So it is a very hectic process at the end. And if you do like this, the thing is not good. So don't cut rivers at the time of extracting samples for condition assessment. So nicely, from that, we can understand that up to how much depth we can, that the concrete is suffering from carbonation. So this is a very nice method. By using this phenolphthalein indicator, we can really find out the depth of carbonation. So now one more parameter also I want to share with you. So this is a that test arrangement that has been done in IIT Madras. So they have casted some sample, and they have that exposed these samples to the that carbon dioxide rich environment for getting carbonated. So they kept one set of sample under the that direct sunlight, and one set of sample in a in a sheltered position. So one set in sheltered and one that set in unsheltered position. So here you can see one set in unsheltered, it is open, and one set is in the sheltered position. So it has been seen that after some significant days, it has been seen the samples which were present, which were kept in the that sheltered part suffered from more carbonation. So what is the reason behind it? So naturally, carbonation can occur at 0.4% of carbon dioxide. So when there is the presence of 0.04 percentage of carbon dioxide, you can see carbonation. And what is the reason why the sheltered specimen is suffering from more that carbonation? Because the humidity. So if you see the samples which was there that unsheltered, due to this sunlight, the humidity or the moisture of the sample was getting evaporated, and the samples got dried. In the case of sheltered, it has been you can see that the there was the presence of the required amount of humidity that I already mentioned earlier, that 60 to 70 percentage. So here in this stage, wait 1 minute, I'm showing you again. So in this stage, the amount of humidity is less than, or is less than particular requirement of carbonation. So the carbonation is somewhat less in the unsheltered. But here, due to this shelter, the humidity that stays in that particular samples, and the humidity was in that typical zone of 60 to 70%, and it has been not that severe corrosion has been noticed due to the presence of humidity. So, so again, I already told. So naturally, carbonation can occur at 0.4% of carbon dioxide, and it also depends on the relative humidity and the temperature conditions. If the temperature is more, the relative humidity will be less, and eventually the corrosion will also be less. And if the temperature is less, the presence of humidity will be more, and the relative humidity will be more. So it may also that for that particular reason, the samples which were kept in the sheltered position that shows much more corrosion. So from the basis of this particular test, what they have did, we can see that in this structure, we can see that the carbonation will be more here, because in this particular region there is no that entry of sunlight. So the relative humidity of that particular region will be more compared to the other part which is directly exposed to the sunlight. So here you will get a very less carbonation, but here you will get a very low carbonation. So in any normal conventional building which is not suffering from chloride induced corrosion, if the building is suffering from carbonation induced corrosion, the typical regions will be the shaded region. Suppose if you talk about this sunshade, below the sunshade you will find much more carbonation, or rather than the top of the sunshade, because below the sunshade there is not a direct reach of sunlight, so the humidity will be more here. So due to the presence of more humidity, more corrosion will happen. So these are the things I want to share based on the carbonation induced corrosion. So the humidity and temperature plays a vital role of the that carbonation to initiates and to for the propagation of the corrosion of such types of mechanisms. So to summarize, we can see that in the first lecture we talk about the cost of corrosion, why it is important to know about the cost of corrosions, and we should have a corrosion management. What is the need to manage all those things? Because if we continuously expending that much of huge amount for doing the corrosion work or repair work, it's not good actually. And we have seen the that corrosion mechanism and how it happens in a concrete and that steel structures, that electronic cells, generation of the electronic cells in a concrete structures, how that both anode and cathode can coexist in the same piece of metal. What are the different reasons for this non-uniformity of the structures of the steel, and non-uniformity of the electrolyte, and that how the cracks are inducing due to corrosion. Why the cracks are inducing due to corrosion? Because due to the increase in the volume, it gives pressure to the concrete surface, to the concrete, and if the pressure is more than the tensile strength or tensile stress, we can see the formation of cracks. And after that, we have seen that two major reasons of that corrosion. One is chloride induced corrosion and one is carbonation induced corrosion. And we have seen first the carbonation induced corrosion and the mechanism of carbonation, and how to assess the depth of carbonation, and how the temperature and moisture, and also the that other factors, how it that affects the carbonations. So these are all the references I used, and most prominently I want to mention that the materials from Dr. Radhakrishna G. Pillai from IIT Madras helped me a lot to make up all those things to prepare this presentation. So once again, thank you all of you for attending this webinar. And tomorrow we are going to see the the other parts of this webinar module. And I hope so it will be useful, and the informations that I shared and I'm going to share with you may help you people to recapping all those things. So tomorrow again we are going to see and going to meet in the same time. So all the best and stay safe.